Okay, good morning, everyone. Welcome to the Astro IPARCOS seminar series. It's my pleasure today to introduce you to Isabel Pérez, who I've known for many years already. We met for the first time in the Netherlands at the Captain Institute. I was doing my PhD. He just arrived there from doing her PhD in Australia, supervised by Ken Freeman, and he became an expert in dynamics of galaxies and doing both simulations and numerical simulations and observations. So he became an expert in both areas, which is not very common. As I say, I met her at Groningen at the Captain Institute, and he first got a Captain Fellowship there. And after that, he applied for a Beygu Fellowship, which is a very prestigious fellowship given by the Dutch government. And he spent there a few more years with that fellowship. After that, he moved to the University of Granada, where he's currently working. First with one of those grants to attract talent from the Andalusian government, and then he got a permanent position, and currently he's a professor titular at the University of Granada in 2017. Isabel has a lot of a wide range of interests in the field of galaxy formation and evolution. He's done studies, as I told you before, with numerical simulation, with observation in very nearby galaxies at high redshift. He's done a lot of very relevant contributions in the field of dynamics, stellar populations, and I can many more fields. So today he's gonna tell us about the project Cavity, which is one of the legacy projects that the Calar Alto Observatory has granted this year. So he got 600 nights. So I don't remember the number of nights. He will tell us now. So to understand the influence of large-scale structures in galaxies, and in particular the importance of voids. So Isabel, thank you for being here, and whenever you want.
So thank you, Patricia. Well, it's a pleasure to be here. So first, I would like to thank you all for inviting me and have the opportunity to talk to you about the Cavity project. Let me share with you the slides. See if I can share. Okay, so I'm gonna talk to you today about the Cavity project. Already, as Patricia said, it's a legacy project that I'm leading. But of course, this project, it would not be possible, and I would not be here in front of you telling you about it if it wasn't for the list of people presented here. As you can see, it's a fantastic team formed by the cosmologists and also experts on galaxy evolution and galaxy structure. Both also covering observations and simulations. And it is also interesting that, now we also joining forces with in a multi-wavelength team. For instance, we have all the IRAM, some IRAM participants that will be pushing forward also some ancillary data into the neutral gas content of the void galaxies. So also in red, you can see here that some students that are directly or indirectly linked to the Cavity project. And of course, I cannot forget the Calar Alto staff, which is actually making possible of the observations at the telescope. So my many thanks go to them. So first, I'm gonna give you an overview of the presentation. I would like to talk first about just very briefly about the Cavity project to contextualize it, and to give you a framework to then tell you about why it's important and why we think it's interesting to study galaxy in voids and voids themselves as well. So then I will proceed to give you a more detailed technical details about the Cavity project, the sample, the observations and pipeline, the data products that will be released in the data release, of course, and the status of the project, the current status of the project. So first, let me tell you a little bit about the Calar Alto Legacy Survey, the cavity, which is the Calar Alto Void Integral Field Treasury Survey. And there was just before the pandemic, the Calar Alto Observatory opened a call for new legacy projects and also new instrumentation to set the horizons and the new their science horizons for the coming years. So they opened this call and we participated with this survey, and we were awarded, 3 projects were awarded time, and we were awarded with more than 100 useful nights to use the PMAS IFU, the Integral Field Unit spectrograph on the 3.5 meter telescope. So the aim here is we will analyze these data cubes for around 300 void galaxies. And we already have successfully started almost a year already, well, 6 months. We started since January 2021, successfully observing. So just to give you just briefly, the main goals is, of course, to determine how the environment has influenced the mass assembly of void galaxies. I mean, we expect that maybe the mass assembly in these low density regions have gone in a different way, and that in denser regions where self-gravity actually have accelerated their structure formation. And so we want to see whether this is being slowed down or delayed, and how the mass assembly of void galaxies has proceeded and compared to those in denser regions. Also, in the same lines, to establish how galaxy formation and the properties are dependent on this larger scale environment. And here also, I mean, we will be bringing this ancillary data that I was mentioning before with some neutral gas information to establish whether star formation rates or star formation efficiencies are similar to those in denser regions. And of course, we also know that galaxies come in basically 2 main flavors, those that are forming stars and those that are quiescent. And the movement, so how the galaxies move from these two main blocks of galaxies, is these physical processes are still uncertain, and the pristine environment, the low density environment of voids can offer a good opportunity to understand better the galaxy transformation processes. So I'm going to start talking a little bit about voids now. I mean, you are all familiar with this sort of an image, this 3D cube of a small volume of the universe, where you see that galaxies are not uniformly distributed within it, but it has this sort of a sponge-like structure where you can see walls, some filaments, some clustering, also some lower density regions that we will call voids. Voids occupy around 60% of the space, and I will come back to this number in a few slides. And the sizes are between 10 to 100 megaparsecs inside. So as you see, they occupy basically most of the space, the volume in the universe. And here I'm showing, it's in purpose that to show you some uncertainties about void characterization. I'm showing here the results from a seminal paper by Cautun et al. In 2014, where they applied a very interesting and very sophisticated structure finders, a free scale structure finder in some numerical simulations, in particular the Millennium simulations, and they use this algorithm to find the structures in the universe in these simulations, and they found that the volume fraction of voids, as you can see here in the slide on the right, is around 77%. And the discrepancy, for instance, with the 60% that I showed you before, is part of the problem with voids, and also when you deal with large scale structure, and it is very dependent on how you define the structure. But I want you to take the information, so the idea that voids occupy most of the volume in the universe, but as you see on the left pie chart, the voids in mass fraction, they only occupied 15%. So, and you see the filaments, for instance, in volume fraction are very, very small, but they occupy most around 50% of the mass. So from the same paper also, I mean, there is some information, they concluded some information about how this void evolution, how large scale structure evolved. And well, voids are, the dynamics are dominated by this large scale tidal environment, which actually simplify things to describe void dynamics. And what I'm showing in this figure here is redshift on the x-axis and the y-axis. On the lower panel, you have volume fraction, and on the top panel, you have mass fraction. And the colors are, you have to take a look at the voids, which is the blue. And what is here, basically, that the mass fraction is decreasing with time, and the volume fraction of voids is increasing with time. So there is a flow of matter, in principle, that goes from the voids into the walls, to the filaments, and into the cluster. This is sort of the dynamics of this large scale structure. But, and it is important to note that this is not the last work, but this result is it's been published. Well, it's been this week, and it's by a group in Valencia, doing also numerical simulations, and it's not in disagreement with the previous result, but it's also a caution note that, in fact, what you see here is also the redshift here on the x-axis, and reverse the axis here, and the max flux in the y-axis. So here what you see is some decreated, so the mass, this is only for voids. So this is a mass that is leaving the void, and accreted is mass, gas, or dark matter that is actually being accreted from the filament into the void. And on average, around 10% of void mass at redshift 0, it seems to be accreted from overdense regions. So this is a very interesting result, and it might have some implications for when we interpret data for voids and void galaxies. So if I've learned something from when I have started this work at with the cavity project, is the complexity of defining large scale structure. I mean, depending very much on the algorithms, on the methods to characterize your voids and your large scale structure, you will get a different, slightly different results. It's a result of on the global scale, but the details are different. And overall, it is where the discrepancy is the most at the edges. So when where the structures finish and start. So there is a beautiful work by Libeskind in 2018 comparing the different methods and different algorithms to define voids and large scale structure. So you can have a look at it for a review. And also, of course, these different methods will give a different average density profile. I'm showing at the bottom the two figures. The one on the left is by a paper by Nadatur et al. In 2015, and the right is the Pan et al. On 2012, both on Sloan data. So these are observed, this is from galaxies, real galaxies. So the y-axis is a different how it is defined. In the case of the Nadatur paper, it's just basically the density divided by the average density of the universe. So of course it reaches the average density of the universe at basically 1. And the Pan et al. Paper in 2012, here what it is defined is the density minus the average density divided by the average density, which means that of course is at 0 where you reach the average density of the universe. And -1 when you don't have, basically, is an empty volume. So you see here is the edges at the difference here in the x-axis is normalized the radius within the effective radius of the void. So it's the radius divided by the radius of the void. And of course, this is also is how do you define a void, and the radius of a void in this case is defining a sphere, a volume, a spherical volume. And if you look at the image that I showed you before, it is clear that voids are not spherical, and not only that, but the definition is subtle because you also have substructures within the void. That these subtle and tenuous filaments that can cross the voids, and whether you define that as part of the void or not, well, that's part of how you define voids, and that complicates this. But something that I wanted to point out within this graph on the left, in the narrative one, that this paper actually is talking about the universality of the density profiles in voids. So they compare not only Sloan data, but also simulated data for galaxies with so different tracers for the density profiles for bright galaxies, dim galaxies, for different radius of voids. And in this case, what I'm showing here is the density profile for voids at different redshifts. And what they find is a sort of a universal density profile in all cases. So this is something that I just wanted to mention. So, okay, we've talked a little bit about voids. So why is it interesting exploring the universe with voids? I think this is a very exciting science that can be done with voids. In the last decade or so, there's a focus being put on to how to get some cosmological parameters and study cosmology with voids as probes. And this is by no means my field of expertise, but I find it very exciting, and I hope also the cavity can help and can somehow get involved in some of these works. Well, in the cosmological side, exploring the universe with voids is interesting because these low-density void environments, in these low-density void environments is where the new modified laws of gravity, which are fully dynamical, we deviate more from the general relativity. And they have some predictions and observables that not only about the void structure, but also about the galaxies, the properties of the void galaxies that deviate from those of the general relativity. So that can be a very interesting test for testing modified laws of gravity. So also the void size function, that is the number of voids as a function of radius, seems to be highly sensitive to the dark energy equation of the state. So it also can help to set constraints to dark energy. I mean, I think this is all very exciting since these are really cut-edge things that we need to understand. Other things like the Alok-Paczynski test is a geometric test that assumes some that expects some statistical isotropy of the structures, and it can be also used to probe or constrain the energy equation of the state. And also neutrino physics seem to be, the properties of neutrinos seem to be linked to cosmic void observables such as the cosmic size, cosmic number, cosmic void clustering, void size, void shape, etc. So I think this is very exciting science that can be done voids as independent tests with other tests. And of course, something that is closer to the cavity project is galaxy formation and evolution. And it is, of course, from this low density environment seems to be ideal for studying effects of the cosmic environment, since it's not subject to some of the physical processes that has happened in denser environments. So let me talk a little bit about what we know of void galaxies. This is from some of our own already sample. But this is not new. This is not our result. This is something that I'm showing here, the color magnitude diagram for a sample of void galaxy and galaxies in filaments. And so in the x-axis is the stellar mass, y-axis the G minus R, the color, and the projection histograms on the side. So you see here that in general, I mean on average, void galaxies tend to be bluer, and also they have a different distribution, mass distribution function. So let me show you a cavity galaxy. And well, this is in general when one thinks of void galaxies, seems to think of an isolated galaxies, and something that what I wanted to show here is that the void galaxies are by no means isolated. They reside in low density environments, but that doesn't mean that they are isolated. And in fact, you see interactions, triplets, doublet, pairs, and you see here, this is a deep imaging, it's a color composite imaging that of one of the cavity sample galaxies taken with the INT telescope, and you see here the tidal tail, and on the left you have the Sloan data. This is also we are carrying on a campaign to obtain deep imaging that is led, well, I will mention that later, by René Pelletier and Javier Roman at the IEC. So what else do we know about void galaxies? Okay, so about the neutral gas content, they seem to be similar to that of galaxies that reside in denser environments. What I'm showing here is the CO mass on the y-axis with respect to the stellar mass as a function of the stellar mass. And the empty dots, the red ones, are our sample of taken from the void galaxy survey. This is, let's say, pilot to the cavity project, and it comprises 60 void galaxies. And what we observe, we obtain IRAM data for 20 of them. And underlying is there some galaxies from data from galaxies in denser environments. So in principle, it doesn't seem to be different. There are some hints, and Jesus Dominguez Gomez, a student at the University of Granada, is working on it. Maybe some hints of differences of star formation efficiency for void galaxies. But the problem here is the low number statistics. In fact, that is the problem with most of the works that have been done so far regarding void galaxy properties, and all the uncertainties basically come for that. As it is not clear yet whether void galaxy star formation rates are similar to the counterparts in certain regions. So Beygu, for instance, in 2016, and Moorman concluded that it is marginal. But Ricciardelli in 2014 concluded that it was higher in void star formation rates in void galaxies is higher than in denser environment galaxies. But it's still, well, as I said, probably due to low number statistics. There's also discrepancy about the present metallicity content of gas in void galaxies. And I mean, the two works that are basically the basic works in this subject are based on less than 10 galaxies, and they are all dwarf galaxies residing in voids. And there is also been debates about how, I mean, we know that how the structures grow, the baryonic mass is not linearly related to the halo mass. So it is natural also to question whether there is a difference between the dark matter and stellar mass between void and non-void galaxies. In a work from this year, using manga data, the scientists concluded that the group concluded that there was not a significant difference between the dark matter and the stellar mass. However, this was done in a sample. It's a large sample, the manga sample of void galaxies, but the coverage of the galaxy radius, it was not consistent, so it was different from one galaxy to others, and it was only based with rotation curves in the optical. So, of course, I mean, and basically, I think all the discrepancies about the void galaxy properties reside on the lack of proper number statistics, but also on the proper characterization on the void themselves. So where do they reside, these galaxies within the void? As I said, these are complex structures as well, and they also are populated by these substructures. So knowing where the galaxies are dynamically characterizing the void, I think is critical to be able to interpret the data correctly. So the cavity comes to solve these issues. Of course, what we will do, this is the aim, is to be able to actually determine the properties of galaxies in voids. And for that, as I said, we need a well-characterized galaxy sample. This work is led by Simon Verley here at the University of Granada. Void characterization, and we have in the team the Lyon group led by Hélène Courtois with all these peculiar velocity data sets that can actually dynamically characterize the voids. And also, I think it's critical to have a well-defined control sample. And this is work led by Rim van Wijger. And I think it's as critical as defining a good void sample. So the actions that we will be in practice, we will obtain spatially resolved star formation histories that will help us to analyze the mass assembly of the galaxies. And we also will obtain 2D ionized gas properties, star formation and star formation efficiencies. Maybe we will be able to see some signs of accretion of material. And since we will also have CO and H1 for all the void galaxies, I will mention later about that. Also the relation with neutral gas. And since we have also the H1, we will be able to probe the dark matter content to a larger radii. So for all this, we were awarded 110 useful nights, as I already said, with the PMAS spectrograph on the 3.5 meter. And this work will be done on around 300 void galaxies. So I will talk a little bit about the sample. We have now a model sample of around 1,000 galaxies. This is basically what I'm showing here is a wedge diagram of some of the voids with the Sloan data on the right and a slice on the left, right ascension declination of the projection of a redshift range. So we have selected 15 voids covering different dynamical stages. We want to make sure, be conservative and make sure that the galaxies that we choose are part of the low density regions. And we also avoiding the Sloan edges and redshift below 0.05. As to have a coherent set of data, we want that the 24th isophot, the optical isophot, fits the field of view of the IFU, and we've chosen intermediate inclination galaxies to be able to do all the science that we want. So this is a color magnitude diagram of the sample, the model sample. From this, 1/3 is going to be observed. And as you see, it covers the color diagram properly. And we will try to also, the 300 to populate the color diagram magnitude. So we also want to probe the void. So here I'm showing the normalized distance with respect to the void effective radius and number of galaxies. And here I'm showing a number of histograms. And the cavity observed, all the observable is the pinkish color. The ones that we already observed at this 90, I will come back to that later, is the red one. But of course, we cannot be unaware of the manga data. And we have around 90 galaxies that are actually part of the sample. And of course, we will use that data as well, since it's there. And so the idea, of course, as you see, is covering the whole void radius. So we want to also populate our 300 with the galaxies from all the volume of the void. So the observations, we are using the PMAS with the PPAC mode at the moment, is the instrument at the primary focus of the 3.5 meter telescope in Calar Alto. Many of you are familiar with this instrument, and it has around 330 science fibers in an hexagonal configuration and covers around a minute square as a field of view. And also samples well with 6 fiber bundles with 6 fibers each that conform the sky background sampling. So the instrumental setup and the observing strategy is actually very similar to that that we've carried out with the CALIFA survey. Many of the collaborators of the cavity project have been also members of the CALIFA survey. And we are carrying out the observations in service mode. And in here, I would like to thank all the Calar Alto staff because they are helping us a lot and they're making the whole project possible. And they're really useful. And they're doing a great job. We have a dithering pattern that it was basically similar to that of the CALIFA survey to have a 100% Philip factor of the area. We're using 2 main gratings, the V500, which it was actually purchased for the CALIFA survey, and in fact to obtain also star population and star formation histories, so same sort of aim different sample. And it has this full width maximum of around 6 angstroms. And for some of the brightest, we've learned a lot with the CALIFA survey, and we won't do the V per 100 for all the galaxies because we want to maximize and not waste any observing time at the telescope, and we will do the high resolution for the brightest objects. So around 50% of the sample will be observed with both the V500 and the higher resolution one. And the total exposure times are around 1.5 and 3 hours. So data reduction and the data quality team is led by Ruben Garcia Benito, who's the expert on this, and he did this also for the CALIFA survey. And I'm really happy that he's on board and the team, and we can count on him to do this because it's not a simple task. So of course, with in the data reduction, the error on the pixel is being propagated at each stage. And it's the vignetting due to some loss of transmissivity of some fibers at the edges of the detector, and the scattered lights are characterized, so we can actually include that in the documentation of the data outputs. So careful spectral resolution and wavelength calibration. I'm showing here down two plots. 2 figures showing the instrumental dispersion within angstroms from the arcs, from some arcs taken with the cavity data. And this is, as you see, is just to characterize. In the left, you see this pixel and the fibers. And on the left, just a plot, a cumulative plot of the pixels, of the pixel velocity dispersion. So the aim is to characterize well the quality of the data and to give this as a product as well. So we do as we did for the Khalifa, we anchor the photometry with some photometric data. So let's not forget that that the cavity is a legacy project. So we will be offering the observation and some of the high-level data products to the public. But of course, the product needs to fulfill the science requirements. Stellar population studies are the most restrictive regarding signal to noise. And for instance, I mean, each particular science requirement, of course, have restrictions. And this is now being performed by the data quality team of the cavity collaboration. And as I said, we will be offering all the data products in the first data public release that it will be in 2023. We'll be offering to the public, of course, the data cubes for all the void galaxies that have been observed. We'll be also offering some stellar and gas kinematic maps, stellar population main ages and metallicities, emission line maps, and maybe also abundancy maps to the community in a very well documented, and also this is very important to us, we are preparing a very easy front end for the database to be able to access to all the information. This is actually taking a lot of time, and I will mention that later. So this is just a basic, just some plots that I'm showing. This is one of the galaxies. Is with some information that's useful to us on this sort of radar plot. But just to show you here, for instance, on the bottom left is the central spectrum of one of the galaxies and the zero moment of one of the cavities. This is actually one of the first versions of the pipeline. Now the pipelines is in change. And so the data is probably slightly different. So I will now talk about the status of the project. So far, we've observed almost like 35 nights. So we've gathered like 90 galaxy data cubes, and we've proven the successful observing strategy. And again, here I need to thank the Calar Alto staff. A working pipeline also. A new version is coming soon. The working database that I was mentioning, powered by Daikiri, and this is led by the engineer in the team, Antonio Jimenez, who's doing a great job in developing both all the web page and all the front end on the database. And of course, it's important to the cavity project, it is ancillary data. So we are now carrying out CO, observing campaigns, deep imaging at the INT, and also H1. So the aim is to have this for all the cavity sample. The CO is led by Ute Liesenfeld and also the IRM staff. And the deep imaging is by Javier Roman and René Pelletier, and the H1 by Daniel Espada at the University of Granada. So here you have the web page of the collaboration of the project. It is an open collaboration. If you would like to participate, feel free to send us an email. And if you think that you can offer something to the project and you can get also from it, please contact us. And there will be a postdoc announcement coming soon. So if you are interested in working with cavity, or you know someone who could be interested in working with us at the University of Granada, well, let us know. And finish here, but before I I close the talk, I would like to also mention, I mean, we are doing a big effort on outreach for cavity. And in fact, in particular, we have two groups working on inclusive outreach for cavity. And they're doing a great job developing material for blinded audience and also for the deaf or hearing impaired audience. So I would like to show you and acknowledge their work as well, because it's going to be, I think, great material that will be useful for everyone. And if you don't mind, I will show some promo. It's only a minute. It is in Spanish, but it has the sign languages joined to it. And even if you don't speak Spanish and here, it's mesmerizing to see the signs in the sign languages describing the project. And it's a short one. And also something that I didn't know, sign languages, even in Spanish, is different for the different Spanish speaker communities. So here, thanks to our Chilean connection, we have a version in Chilean and Spanish at the same time. So if you allow me, I will show it to you and finalize with that. Oops, let's see, it's not there. Sorry. Yeah. Let me. Oh, sorry. Let me. I apologize. Well, I don't want to delay more the talk. So if you're interested, I think the best thing would be I will place it back onto on our webpage, and you can have a look at it if you want. But I think it's worthwhile, and they're doing a great effort for this. So with this, I stop sharing my screen, and I will take any questions.
Thank you very much, Isabel. Very nice talk, very nice project. And yeah, I mean, well, there is one question already by Jose Gaite Cuesta. I can read it. She says she's missing a definition of a void, what a void is. And then, yeah, that first question.
Yeah, well, indeed. I mean, it's, as I said, it's not an easy, but it's this region in space that has around 10%. So you define these regions we have around, it's a constant, as I can show back the graph where I show the density profile, but basically they are very much below the average density of the universe. So around 10% of the density of the universe, and these regions will define these low density, volumes.
Okay, thank you.
But as I say, the edges and the contents with the larger scale structure, it very much depends on the algorithm that we choose to define the structures.
Yeah, it's difficult always, it's true. Thank you. Marisa has a question, and you can actually open your mic and do it yourself, Marisa, if you want.
Hi, Isabel. Thank you very much for your nice talk and also for the inclusive material issue. I will see. I have a question on metallicity of the galaxies in the void, because you have mentioned all these papers with different opinions about that, and in fact, in all papers they say that the low metallicity galaxies were not that often in the void. But anyway, my question is if you have a limit of metallicity for which, with your current exposure times, you can derive a direct metallicity from the oxygen 3 lines, or if you have otherwise a limit of the oxygen 2 lines.
Well, it's a good question. I don't have the answer right now here. But I mean, I think it very much depends on, the ionizing also properties of the gas there. And but I mean, look at that, we are exposing for 3 hours on some of the galaxies. So certainly we'll have, and the redshift is not very high, 0.05. So we'll be as sensitive as, for instance, the Khalifa survey for the metallicities. I don't know if this is helpful for answer to your question.
Yeah, thank you. But I know it's very hard to detect the low metallicity because they have the star formation and the oxygen 3 line in these galaxies is very, very weak.
Direct method, I'm excluding direct. Well, no, not excluding them because we might have some auroral lines. But I mean, in principle, I think we'll be in principle relying on indirect methods for determining the abundances.
Okay, thank you very much. I have a little question. Is that the void number 12 from Pustil included in the sample?
I don't know. That's a good
okay, no, because it's a void in which they have measured a lot of metallicities for the lowest metallicity galaxy. Yeah, just to know, just curiosity.
Yeah, no, it's a good question. I will.
Okay. I will write you later. Okay, thank you.
We didn't. The limitation for choosing the voids, it was not voids that were observed, but it was the what we wanted to do with the science. So they were not predefined and in any way.
Okay, thank you very much.
Thank you. Is there any other question? You can raise your hand. Well, I have one. Had you made a study of how complete is the sample, like in terms of the maximum volume, something like that?
Well, yes, I don't think we expect to have a complete sample. It's like completeness is not the aim of choosing the sample, but more of characteristic on the void galaxies.
Okay.
So that's why, for instance, if we want to map the color magnitude diagram, we already imposing some incompleteness to the survey.
No, yeah, no,
that's not probing the same way like lower and higher masses in void galaxies.
Okay, fair enough. Thank you. Mark, you can open your mic and ask Isabel.
Yes, hello. Hi, Isabel. Thanks very much for a beautiful talk and a beautiful project. Really excited to see this starting to get data. My question was on the analysis as a function of local density of the galaxies. So a void, putting a galaxy in a void means that you're relating it to a density on a scale of whatever, 100 megaparsecs or so. Would the properties perhaps could they be studied on a scale versus density on a smaller scale, of the size of a group of galaxies, scale of like 10, 1, 2, 5 megaparsecs?
No, I think it's interesting. So we are not choosing specifically like triplets or doublets or small groups for that matter, but we already have small groups and triplets. As you see also on the INT image, we have not isolated galaxies. So your question is how to disentangle processes. Well, we can compare statistically with those local densities, higher local densities in denser large volumes, to see if the properties, like for instance, maybe indeed the metallicities will be different, or we can compare within voids whether in the lower density, local density towards the higher density. This is a very complex. I realize, but it is so. I think it's an important point what you make. And I think it's part of where the problems that have been so far in interpreting void galaxies is that these things have been neglected. Well, not neglected, maybe just they didn't have enough galaxies to be able to look upon these other things. But we have that in mind. So we already like characterizing groups and density.
Exactly.
So
the question would be a local group inside our local group. If we find something similar inside a void, how distinct is it from ourselves for falling into Virgo?
I'm not sure whether we'd be able to distinguish something to determine if one of the groups that we see, because we are of course biased to bright galaxies. So I don't know whether we'll be able to make the equivalence to the local group so easily, and also the dynamical state of the group. So yeah, it's not even simple in nearby groups to actually determine whether they're equivalent to local group to the local group or not. So, but it's an interesting, yeah, within voids to look at the denser regions and whether they are actually linked to these substructures and tenuous filaments within the voids, for instance, on some the neutral gas, for instance, as well. I think that will help us also to get interesting information. Yeah, this is exciting.
Mark, how are things in La Palma?
Yeah, I was going to ask.
Oh, yeah. You may have seen I sent a message yesterday. We decided to close our telescopes because we had a bit of a dust rain. It's like sand from the beaches. Many of you have been in the beaches of La Palma. There's this very nice black sand. So we got that black sand raining on us on the telescopes, and for that matter, everywhere at home too. Yeah, it's tragic. As you all have seen the footage on the news, I'm sure. On the first day, it was very exciting. I drove as close as possible to the telescopes. I saw the flames. I saw the rocks, the incendiary rocks going up and falling down in these beautiful parabolas, and all the smoke and the noise, a tremendous noise. It was really impressive. But of course, 3 or 4 days later, then you start seeing the consequences. We have 2 members of our staff who have houses nearby. The houses are still up, but of course, it's very tricky. We don't know. It's been only 5 days, and this is going to last a few weeks. So yeah, thanks everyone for your expressions of support. I've received many of them, and we'll keep informing you guys.
Thank you, Mark. Yeah, and all the best. Hopefully, yeah, the staff can keep their houses and everything like get back to normal. So.
Yeah, thanks, Patricia.
All our thoughts are with you and all the people at La Palma, friends and colleagues.
Yeah, we will. We're still going to the telescopes. We can drive. There's no problem going up there, and we're working as normal. As you know, at the ING, we are working very hard on getting WEAV up. There's still some work to be done, and we're working as hard as we can, and work is progressing well. We have good news for all of you. You are the ones who will be doing the science. The good news is that we have brought down the detector readout noise to very good numbers, to what we desired. So because a lot of this data will be read noise limited because it's high resolution. This is very good news. So this will add a lot of value to the quality of the spectra.
Indeed, very good news. Thank you. So, okay, is there any other question for Isabel? It's your last opportunity. Raise your hands or just open your mics and talk. Well, then, let me thanks again, Isa, for giving us this talk and for presenting this very nice project. I'm sure it will bring a lot of very interesting results. Yeah, thank you again.
You are part of it, so.
Thank you to all of you who has connected. Well, there is one last minute question from Miguel Sánchez Portal. Miguel? No, he was clapping, sorry. Yes, sorry. He's just clapping, he was not raising his hand. I saw something yellow. Okay, then, well, thank you to everyone for joining as well, and to those joining through the YouTube channel, and see you next week. Another seminar, I don't remember now which one, but it will be announced soon. Ciao.